Here we're looking at a data table for the reaction of BrO3 with bromide and 6 hydrogens to give us bromine and water. Again, that reaction provided on the previous page. This time all 3 reactants are given, and I have reaction rate data for each of these trials. So I have a trial 1, 2, 3, and 4 that we can use to compare, knowing that we're looking to find the rate with respect to each of the reactants. So rate is equal to K times the concentration of BrO3 raised to some order yet to be determined, times the concentration of Br raised to the order yet to be determined, and H plus, same story. Here we have 4 sets of data, and I'm going to stare down and try to find best I can where 2 of the reactants are held constant and only 1 is changing. And I can see that pretty quickly between trial 1 to trial 2. 2 of the reactants do not change. The first reactant is doubled. So the only thing influencing the change in rate is our first reactant. Again, notice that I have a -4 power and these are -3 powers. I want to just make sure that I'm looking at them in the same way. So I'm going to make this guy be 0.8. 0.8 times 10 to the -3. And that way I only have to consider the following numbers. 0.8 compared to 1.6 compared to 3.2 compared to 3.2. It's just an easier way to handle that data in my mind at least. When I notice that BrO3 is doubled from trial 1 to trial 2, 8 doubled gives me 16. 8 times 2 is 16. The rate doubled as well. I bet you determined that it's first order with respect to bromate, BrO3 negative. Trial 1 to trial 2 is useful in finding the first reactant. I notice between trial 2 and 3, I'm holding 2 reactants constant and only changing bromide. I'm doubling bromide, the other 2 are left constant. Therefore, the only thing influencing the reaction rate is the middle guy, bromide. If I'm doubling the concentration, what happens to the rate? Doubling the concentration over here doubled the rate as well. In my head, I go 16 doubled is 32. 16 times 2 is indeed 32. So these are indeed factors of 2. So doubling the concentration doubled the rate. It's first order with respect to bromide. One more to determine. Can we find a place where they're held constant? Oh, I see it. Trial 1 to trial 4. Trial 1 and trial 4 hold the first 2 constant, so they are not influencing the rate, but I'm doubling the hydrogen. So the last guy is the only one influencing the reaction rate. What happens to the rate from trial 1 to trial 4? 3.2 over 8, I guess I'd go 8 into 32, comes out to be 4. So doubling the concentration made the rate go 4 times as fast. That's a second order with respect to hydrogen. First order with respect to bromate, first order with respect to bromide, second order overall. We were also asked to solve for K, the rate constant. And for no other reason than it's written first, I tend to use the first trial. The rate of 8.0 times 10 to the -4th molarity per second is equal to K, that's what our target is, times the concentration of bromate from trial 1 to the first power, times the concentration of bromide to the first power, times hydrogen to the second power. Solve for K. We would hit 8.0 E -4 divided by 0.1 to the first power, divided by 0.1 to the first power, divided by 0.1 squared, and we come up with a number 8. This has a rate constant of 8. And let's consider units. The concentration unit here is molarity. Remember the formula, 1 minus the overall order tells us with what respect to raise molarity. Well, we have first order from bromate, first order from bromide, second order from hydrogen. That's a total of 4. 1 minus 4 gives us a value of -3. Molarity to the -3rd, time here is in a second, and it's set under also, so we go second -1. So that would be writing 1 over molarity times molarity times molarity times second. Instead of writing it this way, we'll see it written in terms of molarity to the -3rd, second to the -1. You now have enough ammunition to go through and try Lesson 2.